The research paper discusses the concept of asynchronous federated learning, AFL, and its advantages over classical synchronous federated learning, SFL. AFL allows the server to aggregate the model once it receives an update from any client, eliminating the need to wait for updates from multiple clients or a specified amount of time. This approach addresses the straggler problem in heterogeneous environments where clients have small computational capacities. The paper proposes a new AFL framework with client scheduling and model aggregation, which considers both computational capabilities and fairness. The framework aims to address the staleness problem by selecting one client to upload its local model in each global iteration and then sending the newly aggregated global model back to the client that just completed its local model update. The paper also provides a comparative analysis between AFL and SFL, highlighting the timely updating of the global model as a significant advantage of AFL. The proposed framework is designed to achieve the same accuracy performance as SFL while accelerating the learning process, especially in its early stage. Here is a combined summary of pages 3 and 4 of the research paper. In the context of federated learning, two approaches are discussed: synchronous federated learning, SFL, and asynchronous federated learning, AFL. In SFL, clients perform local learning, and the server aggregates the models from a predetermined number of clients or when a specified time limit elapses. The global model is updated using equation 2, where alpha m represents the aggregation coefficient of client m. In contrast, AFL enables faster clients to proceed with local learning without waiting for slower clients. The server initiates the aggregation process as soon as a model is received from a client, and the global model is updated using equation 3. The key difference between SFL and AFL lies in their learning procedures. SFL has extensive idle time, whereas AFL continues learning without idle time, resulting in faster learning. In a homogeneous scenario, where each client has identical computational capabilities, the total completion time for one round in SFL is tau sin underscore ho equals tau d plus m tau u. Whereas in AFL, it is tau a sin underscore ho equals m tau u plus m tau d plus tau. In a heterogeneous scenario, where clients have different computation capabilities and channel conditions, the completion time is primarily dictated by the computation duration of the slowest client. The disparities between AFL and SFL contribute to AFL's faster learning pace but can also lead to model staleness among slow clients and potentially hinder the convergence of the global model. To address this, it is crucial to identify the effective aggregation coefficient, beta, and implement client scheduling during the learning process. The proposed algorithm utilizes the SFL aggregation coefficient in AFL and introduces an AFL algorithm designed to attain comparable learning performance to SFL. Finally, a client scheduling and model aggregation framework in AFL, CSMAAFL, is proposed to promote convergence and minimize the impact of model staleness. In the context of asynchronous federated learning, AFL, the relative importance of a client in terms of its model's contribution is represented by alpha m. When using the relative number of samples on each client as the aggregation coefficient, the influence of initially selected clients diminishes as iterations progress. The client scheduling sequence phi 1, phi 2, phi m is crucial, where phi I indicates the client scheduled to upload its local model in iteration I. Equation 3 illustrates the aggregation process, which involves a diminishing influence of the initially selected clients. To achieve comparable learning performance to SFL, AFL needs to adopt the same client scheduling strategy and aggregation coefficient. A client is scheduled to upload its model again only when all other clients have finished uploading theirs, prioritizing faster clients. The aggregation weight beta varies in each global iteration, ensuring clients contribute equivalently. The proposed CSMAAFL incorporates a model aggregation scheme, prioritizing clients with older models when they complete their local computations simultaneously. This approach ensures all clients have a fair opportunity to contribute, regardless of their computation speeds. The algorithm is designed to strike a balance between the current global model and the uploaded local models, accounting for staleness through a moving average. The simulation results demonstrate the effectiveness of CSMAAFL in both IID and non-IID scenarios, with the impact of the constant gamma on the results analyzed and discussed. The research introduces a client scheduling and model aggregation scheme for asynchronous federated learning. It considers both computation capability and fairness of clients in scheduling, addressing individual client contribution and model staleness in model aggregation. The scheme accelerates the federated learning process during initial stages while achieving comparable performance to synchronous algorithms. The study employs convolutional neural networks, CNN, on MNIST and fashion MNIST datasets under IID and non-IID scenarios. The proposed CSMAAFL scheme is compared with FED-AVG, showcasing faster convergence in some scenarios. The choice of a constant value for gamma affects the performance, with optimal results achieved in different scenarios. The study concludes that the proposed scheme can effectively accelerate the federated learning process. Here is the combined summary. The authors discuss the shortcomings of existing asynchronous federated learning (AFL) methods, specifically in edge computing systems where resource constraints and non-independent and identically distributed, non-IID, data are prevalent. They highlight the importance of adaptive weight aggregation to tackle these challenges. The authors draw inspiration from previous works, including 4, 5, 6, 7, 8, and 9, which have addressed AFL in various contexts, such as edge devices, geospatial applications, and wireless communication networks. The authors emphasize the need for an efficient AFL framework that can adapt to heterogeneous edge devices and non-IID data distributions. They propose an adaptive weight aggregation strategy, which leverages the Euclidean distance between local model updates to assign weights. This approach allows for more accurate and robust model aggregation, even in the presence of resource constraints and non-IID data. The authors also discuss the importance of asynchronous communication in AFL, which enables edge devices to update their local models independently, without waiting for other devices to finish their updates. This approach reduces communication latency and improves the overall efficiency of the AFL framework. The author's proposed framework, Async-Feded, is designed to address the limitations of existing AFL methods. Async-Feded incorporates an adaptive weight aggregation strategy, which takes into account the Euclidean distance between local model updates. This approach enables more accurate and robust model aggregation, even in the presence of resource constraints and non-IID data. The authors provide a detailed analysis of async-feded, including the mathematical formulation of the adaptive weight aggregation strategy and the asynchronous communication protocol. They also present experimental results, which demonstrate the effectiveness of async-feded in various edge computing scenarios.